Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. The series we're in is called Individual and Social Choice. This is the fourth installment in the series. Last time I started to go a little bit long. I was talking about choice and utility, but I didn't really get to the utility part. So I guess I'll call this installment more on choice and utility. So last time we formalized the optimality principle in terms of maximality. Okay, so given a feasible set, the decision maker will or should choose an alternative that's available, such that there is no higher ranked alternative that's also available. All right, so that's an important idea. The topic I want to cover in this installment is the idea of a utility function, which is really not adding something substantially new. It's just another way of thinking about preferences. So given a preference relation P, what's the utility function? Well, in the formal theory toolkit series, we talked about utility functions. It's just an assignment of numbers to alternatives such that better alternatives have higher numbers or higher utility. Okay, so it's really just a numerical way of thinking about preferences instead of a binary relation way. So what I want to make the point that the utility function is not really adding anything to the model. It's just another way of thinking about preferences. So I'm going to use the term representation. So a utility representation of the strict preference relation is it's a function u such that the following holds for any two alternatives, x and y. If x is better than y, so it's above y in this person's ranking, then it has a higher number. And vice versa. Okay, if it has a higher number, then it has to be better. So I'm actually going to use this logical biconditional statement. So it means that a strict preference holds if and only if the utility from x is higher than the utility from y. Okay, this is a definition, so I'll underline it. Let me add a little bit of notation here that maybe you've seen or not. But when we're talking about a function, it's good form to say what the domain of the function is. That is, what's the function defined on? What does it take in its arguments? And here, it's defined on the set of possible choices. And what does the function give us? Well, in this case, it's giving us utilities. It's giving us a number. It's giving us real numbers. And so we use this notation here, and we put in a colon. And so that, it's just a function, but we're identifying the domain and the range of the function. All right. One other item here to include, we can just use the term utility representation for now, but a lot of times. People will say ordinal utility representation to distinguish it from other ways of using utility, okay? We're only using it as just a way of encoding this strict preference relation, just, you know, encoding these binary comparisons that the decision maker makes. And so it's called ordinal as opposed to cardinal. So I'm not going to worry about saying ordinal every time, but if you've heard that term, that's what we're talking about. Okay, so utility representation is defined by this biconditional. Now, let's give some examples here. Suppose we have our usual example is ranking A above B, C, and D, and E. All right, instead of using a ranking or a graph, we've done both types, right? We can use a utility function, and for that, I'm going to just create a little table here. Left-hand column, I'm just going to arrange the alternatives. And the right-hand column, I'm going to assign numbers to those. So let's do some assigning. We could give A a 5 and B a 4 and C 4, D let's say -1 and E -1. All right. You can tell the way I did that, there was a little bit of randomness in it, but let's just check that this is a valid utility function or representation for this preference relation, okay? Technically, we would have to look at every pair of alternatives, okay? Everywhere there's an arc over here, we'd have to make sure that the utility for the first alternative is higher than the second and vice versa. So we're not going to go through every pair, but let me fill this in. So if we compare, let's say, A and B, A is better than B, so it should have a higher number. And it does. 5 is higher than 4. How about C and D? Well, C is better than D, so it should have a higher number, and it does. 4 is bigger than -1. What about B and C? Well, in that case, there's no strict preference either way. So we can't have an inequality, a strict inequality either way, right? Well, that means they have to have the same number. And they do. They both have a utility of 4. Same with D and E. There's no strict preference between them in either direction, so they have to have the same number, the same utility, and they do, -1. All right, so everything checks out. That is a valid utility function. If I had put in a 3 though for C, this wouldn't work, right? Because here we have 2 alternatives. One has a higher number than the other. B has a higher number than C. So if this were a utility representation, it would have to be that B is strictly preferred to C, but it's not. Right? So we can't put a 3 in there. It has to be the same utility as B. Right? You get the idea. But also you can probably see that, well, there's other utility functions that would work. Okay, so let me put a squiggle or a tilde above this one. Let me just pick some other numbers here. How about 1,000 for A, 0 for B and C, and -33 for D and E. That's fine. That works. You can tell, you can fill in these numbers in lots of different ways. In fact, if P has an ordinal utility representation, then there's an infinite number of representations that it has that you can get just by changing the numbers around, as long as you don't, change the ordering of the numbers. Now, you can, if you don't want to use a table, if you want to think about things graphically, I should mention you can also do that. Now here I'm going to use the horizontal axis for the alternatives. Even if they're not numbers, I'm just going to put them here in alphabetical order. And then I'll use the vertical axis for utility. That's not gonna, it's gonna be kind of messy, but anyway, let's do this. So in that first example of utility function, I gave A a utility of 5 and B and C had a utility of 4. And I can just indicate that, by plotting points. This is the graph of the utility function, okay? It's not a smooth kind of graph, right? But the domain of this function is not the real line, it's just these 5 elements that I've put on here. So, and we gave D and E a utility of -1, okay? So, so even though it's kind of funny looking, we're just plotting points instead of drawing a curve, you can still graph a utility function. So all right, let's think a little bit more about the indeterminacy here of our choice of utility representation. As I said, you can really move these points around any way you want, as long as you're not messing with the orders of these things. Okay, so the blue dots would also be a perfectly fine utility function. So let me introduce an idea here. Now for this, I'm going to take a function that's defined on the real line. Let's call it f. And we'll say that f is increasing if the graph looks like this, so it's sloping upward. Formally, we would say for any two real numbers, x and y, if x is less than y, then f of x, I need to write the then part, if x is less than y, then f of x is less than f of y. Okay, you can see that property holds here. If I take x less than y, then f of x is less than f of y. So that's just sort of how we would formally define the idea of a function with an increasing graph, a graph that slopes upward. So suppose I have a utility function let's take the black one here. So the utilities were, we assigned -1 to D and E. Oh, sorry. And we assigned 4 to B and C, and we assigned 5 to A. Now, right, so this is the, I should just write this down. Now, let me take an increasing function. Could be any increasing function, f. And I'm going to apply f to the utilities. All right, so so what's the value of f at -1? Well, it's this value here, right? That's f of -1. What's the value of f at 4? Well, it's this over here. The value at 5 is this. Notice that because this function is increasing, I haven't changed the orderings of any of these utilities, right? -1 is less than 4, and f of -1 is less than f of 4. 4 is less than 5, and also f of 4 is less than f of 5. All right, so why am I doing this? Well, the point is that if we take the utilities of these alternatives, and then I apply f to them, right? So I'm going to take the utility from A and plug it into f. I'm going to take the utility of B and plug it into f, and so on. I'm just going to do that with all of these. Remember, U is a utility representation, so whenever one alternative is preferred to another, it has a higher utility. Well, that's also true if I then plug those utilities into f. Okay, so if I take f evaluate the utility from A, that's going to be bigger than f evaluated at the utility from B. That's going to be the same as f evaluated the utility from C. Let me actually write that. So what this does is it gives us a different assignment of numbers to the alternatives, but the conditions for a utility representation still hold. Okay, so all right, I'll stop talking about it and just state another proposition. Okay, so so given any strict preference relation P, if U is a utility representation of P, and if f is an increasing function, and here I don't have to, I can be a little bit more general, but here I'm just assuming that f is defined on the whole real line, let's say. Right, so f is a function that you plug in numbers and it gives you back a number. And let's suppose that f is increasing. Right, that's a long statement. If U is a utility representation of P, and if f is an increasing function, then if I compose the functions, right, so now instead of just the utility from x, I apply f to that, right? So it's f of utility of x. This is also a utility representation of P. Okay, and that's because it doesn't change the ordering of the utilities. Okay, this gives you an idea of just how indeterminate the choice of a utility representation is. I can take any increasing function and apply that to u, and that'll give me another utility representation. So, you know, if I say the utility representation, I really mean a representation. This is kind of an abstract point, but when you're doing rational choice modeling and working with utility functions, it's good to understand there's nothing inherently important about a particular choice of utility function. You can choose, you know, a zillion different utility functions to represent the same preference relation. Sometimes we'll make one choice just because it's analytically convenient, but there's nothing that's you know, fundamentally special about that. All right, so the last thing I want to do is actually understand when utility representations exist. In fact, it turns out that they exist quite generally, okay? We're not going to do the most general proof here, but pretty much in any model that you're going to think about, you can use a utility representation of preferences. All right, so let's assume that the set of available choices is finite. And, you know, so to that extent, we're not super general, but it can be as big as you want. Then P has a utility representation if and only if it's a weak order. Okay. Remember, that means that it's asymmetric and negatively transitive. Okay, so this is it's an if and only if statement here. So what that means is that this result, assuming a finite number of alternatives, gives us a complete understanding of which preference relations have utility representations, okay? Because it's an if and only if, it goes both ways. So to prove this, when you have an if and only if statement, remember we have this logical notation for it, the arrow pointing in two directions. You can, well, another way of thinking about this is that this is the same as two logical conditionals pointing in different directions, okay? So sometimes the way to prove an if and only if statement is to prove these logical conditional statements in both directions, okay? So first let's do I call it the left to right direction, okay? That is, I'm going to show that if P has a utility representation then it's a weak order. All right. So when you're doing this, when you're proving a logical conditional, you want to take on the antecedent as an assumption. We're going to suppose that P has a utility representation. We'll just follow convention and we'll use the notation U. So let's suppose that U is a utility representation of P. Well, let's show that P has to be asymmetric. So consider any alternatives, A and B. So asymmetry means you can't have strict preference going in both directions. All right, so that's what we need to show. So obviously, just by properties of the real numbers, it can't be that the utility from A is bigger than the utility from B, and the utility from B is bigger than the utility from A. That's not how strict inequalities work. You can't have a strict inequality going in both directions. So that means remember a strict inequality, if A has a higher utility than B, that's the same as being preferred to B. That's what a utility representation is. So we can't have A preferred to B and B preferred to A at the same time. So P is asymmetric. Next, we need to show that P is negatively transitive. And to do that, we're going to consider any three alternatives. And we'll suppose that the antecedent condition of negative transitivity holds. We'll put A in for X, B in for Y. So we'll suppose A is strictly preferred to B. And we need to show that either A is strictly preferred to C or C is strictly preferred to B. All right. Now we're supposing A is strictly preferred to B. We're assuming U is a utility representation. So that means since U is a utility representation, that means that the utility from A is bigger than the utility from B, strictly bigger. All right. Now, of course, the utility function assigns some number to C as well. And we're going to consider two cases. There's two possible cases. Either the utility from A is strictly bigger than the utility from C, or it's not strictly bigger, which means that it's less than or equal to the utility from C. All right, one of those two things has to hold. In the first case, since U is a utility representation of P, and A has a higher utility than C, well, in the first case, that means that A is strictly preferred to C. In the second case, let's put two things together here. In the second case, the utility from C is at least as big as the utility from A. And we just noted that the utility from A is strictly bigger than the utility from B. And if we just connect those inequalities, that tells us that the utility from C is strictly bigger than the utility from B. Again, since U is a utility representation, this implies that C is strictly preferred to B. So we've shown that, in either of these two cases, well, in the first case, A is preferred to C. In the other case, C is preferred to B. So we know that the desired condition holds, right? And this implies that P is negatively transitive. In other words, it's a weak order. So this completes the first half of the proof. This is the left to right direction. We still have to do the right to left. That actually is the more interesting half of the proof, but I'm way over time, so I won't try to do that now. I'll push that to the next installment, and we'll finish everything I wanted to say about utility functions there, and I'll see you there.